Hi everyone, two remarks are in order after proving the strong law of large numbers. The first one is some kind of a reversal of the strong law of large numbers. Strong law of large numbers backwards in some sense. So assume that we have x1, x2 and so on, IID random variables, and assume that 1 over n, the sum of the first n, converges to some real number c, where c is a finite real number, so c mod is finite. Assume a deterministic constant, okay, not random. So in that case, let's do a little calculation. Take a look at xn over n itself. Okay, what is that? So what is xn? It's Sn minus Sn minus 1. S is the sum of the first n of the x's, so this is exactly Sn. You can express x as the increment of the sum, which I can also rewrite as Sn over n minus n minus 1 over n times Sn minus 1 over n minus 1, just by extending this by n minus 1. Now the assumption is that 1 over n Sn converges to c. That's what we assumed. So this will go to c, this will go to 1, and of course Sn minus 1 over n minus 1 also will go to c. All of that is almost sure. Let's assume that this is almost sure. Okay, which means that we have c minus c equals to 0, almost surely. Okay, xn over n goes to 0 almost surely. What does that mean? That means that xn minus n will not exceed 1 infinitely often. xn mod over n larger than 1 happening infinitely often, infinitely many times, has 0 probability. But this is of course the same as the probability that xn mod is larger than n infinitely often. This still has 0 probability, so almost surely only finitely many times we see xn exceeding n. Okay, now these guys are independent, so Borel-Cantelli applies, Borel-Cantelli 2 applies, and tells us that it follows that the sum of the probabilities of these events must be finite, because Borel-Cantelli says if you have independence and this sum is infinite, then the events happen infinitely often, which is not the case. So this is finite. Okay, and if you recall the lemma, we had this probabilistic lemma. Let me bring that up. The probabilistic lemma told us that if you have this finite, then the expectation is finite for a non-negative random variable. Of course, I'm going to apply this for the mod of the xn. Okay. As before, you can as well replace the index n by 1. Let me do this in a different color. You can replace this by 1 because the guys are IID, so it doesn't matter which x you're talking about. And then applying this lemma which I just showed you, it follows that the expectation of the mod of x1 is finite. If the expectation of the mod of x1 is finite and we have IID random variables, then immediately the strong law of large numbers kicks in. So once we have that, strong law of large numbers applies. And as soon as we have that, then we know that 1 over n sum of the xk's will have to converge almost surely, because we have independence, we have finite mean, to the expectation of the x1, okay, by the strong law of large numbers. However, we also assume that it converges almost surely to c, and it therefore follows that the expectation of x1 is C. So this remark tells you that if you have IID random variables and the mean converges almost through to a deterministic constant, then the random variables must have a finite mean, and this deterministic constant must be equal to that finite mean. So it's kind of a reversing of the strong law of large numbers. My second remark is the following. Here is the statement of the strong law of large numbers, which starts with assuming a finite mean. What if we do not have that? What if we have an infinite mean? So suppose, another remark, what if we have random variables x1, x2 and so on, IID, but the expectation of the positive part of each of them is infinite, while the expectation of the negative part is finite. This is to say that we do have an expectation. The expectation exists, it's not non-existent, but it is infinite. So E of x1 is infinite. What can we say then? Now here is a line of arguments. Define for any fixed C, not random, positive, define S and C as the sum of the truncated random variables. This truncation might be a little bit familiar, except we don't have the mods this time. So look at the truncated random variables and notice that since C is positive, the truncation only happens for above the level of C, so the negative part of these truncated random variables is the same as the negative part of the original xi's. The positive part is different, okay? But in any case, the xi truncated at most C is definitely smaller than or equal to the xi itself. Okay, when the xi is negative, then the truncation doesn't do anything, so they are equal. When the xi is positive, then the truncation might decrease the value if the value is too high. And with this observation, I can look at Sn over n. Now I don't know if this thing converges. Okay, this I don't know, but for any case it has a limit. As n goes to infinity, everything has a limit. And because the xi is larger than or equal than the truncated version, the Sn using the xi, so the Sn is the sum of the xi. Let me put this in writing. So the Sn is the sum, and of course this is up to n, and this is also up to n. The sum of the xi is the Sn, the sum of the truncated xi is the Snc. So clearly, if the xi's are larger than equal to the truncated versions, then Sn will be larger than or equal to the Sn of the sum of the truncated versions. So therefore Sn over n is larger than the truncated version Snc over n, and therefore the limit is larger than the limit. Okay. Now if you look at the truncated version, then this truncated random variable has the same behavior on the negative side as xi, in particular e of the xi truncated minus, so let's look at xi truncation at C, and then a negative part and then an expectation. That's still finite. In fact, the negative part of the truncated version is equal to the negative part of the original version, because the truncation only happens on positive. Okay? But if you look at the positive part of xi truncated at C, the positive part of this thing, under the expectation, in fact the positive part itself, can never exceed C. Whenever the random variable xi would be larger than C, the indicator kills it. So that's certainly less than or equal to C, which means that we do have a finite expectation of the truncated version. Xi less than C, even under the mod, is finite. And of course these guys are IID. Of course the xi and truncation are IID as were the original xi's. These people are IID with a finite mean, which means that the strong law of large numbers actually kicks in for the truncated version of the things. So we know that the truncated sum over n converges almost surely to the expectation of the truncated variables, which is xi under this truncation. Let's use x1, it doesn't matter. Okay, so in fact this limit actually, it's not only a limit, this actually has a limit for every given c, and that limit is equal to the expectation of xy and xi, x1 essentially, x1 on this event that is not exceeding c. Now if I only look at these random variables here, then these random variables are non-decreasing. These guys are non-decreasing as a function of c, and they in fact even have a limit, namely, just fix index 1 here, namely, as c goes to infinity, with probability 1 x1 is finite, and as c goes to infinity, eventually the indicator will hold true, in which case the x1 goes to x1 with the indicator goes to x1. And also they are bounded from above by the positive part of x1 and from below by the negative part of x1. Okay, and therefore monotone convergence applies. You don't even need bounds, you just need bound from below. Monotone convergence applies since x1 on the indicator is bounded from above by bounded from below. Well, let's put the negative part, it doesn't really matter. Bounded from below by minus the negative part of x1, and that has a finite mean from below. So monotone convergence applies and tells us that if we have a limit going to x1, then the expectation also increases up to e of x1, which is infinite. So what did we conclude? We concluded that the SNC over n goes to infinity, converges almost surely to this constant for every c. For every c we have convergence to this number here. As c goes to infinity, I can get this to go to any large number I wish, because it converges up to the infinite expectation of the x1. So this can be as large as I wish in c, which means that this limit can be as large as I wish in c. Now the left hand side, the limit of the original Sn over n doesn't have c in it, so taking a large c, I can make this as large as I want, and therefore what I conclude here is that the limit of the, so I conclude that the limit of the Sn over n can be made as large as I wish by picking c. In other words, since it doesn't depend on c, it must be infinite. And that's what I expect, because the strong law of large numbers, if the expectation would be finite, would tell me that this sequence converges to that expectation. If the expectation is positive infinite, then still this Sn over n limit is equal to that expectation, which is infinite. So the strong law of large numbers keeps holding when you have an existing but infinite mean. Of course, you can repeat this argument on the negative side as well.